So our next speaker is Dr. Anne-Marie Broomhall from the University of Warwick, and her talk is entitled, Is the Sun's Magnetic Activity Cycle in Transition? Insights from Helio and Asteroseismology. Anne-Marie.
Thank you very much for the invitation and opportunity to talk to you here today. So I'm going to start off by providing a brief introduction to solar and stellar magnetic activity cycles, and then going to tell you what we can learn about the sun's magnetic activity cycle from helioseismology before showing you some recent results that we've had where we've compared the last couple of activity cycles. And then I'm going to move out to the stars and tell you a little bit about what astroseismology can tell us about stellar activity. So this is one of my absolute favourite images of the sun. If nothing else, anybody studying the stars out there can just look at that and see how beautiful it is. So what it is it's showing you images from SOHO, one taken for every year from 1996 all the way through to 2017. And we can clearly see the sun's activity cycle on there. So in 1996, we were in a solar activity minimum. As the sun's magnetic activity ramped up to 2001, you can see immediately the change in appearance, the number of bright points or active regions. The sun's magnetic activity then declined into the long extended minimum that I'm going to come back to later on in the talk. We then rise up to maximum around about 2014, but even just looking here, we can compare 2014 to 2001, and again you can see that the activity maximum in 2001 was much stronger than the activity maximum in 2014, and then going down into the current activity minimum. But as you all know here, the sun is a star, and a fairly typical star at that. So one of the ways we can measure magnetic activity in the sun is looking at the chromospheric activity, and we can see the 11-year solar cycle in the data. Now, other stars, like this one over here, also show activity cycles. So this is data from the Mount Wilson HK project. But other stars don't show nice activity cycles. They show much more chaotic variability in their magnetic activity, and other stars still show almost no activity variability whatsoever. These stars are often referred to as being in a Maunder minimum-like state. And one way in which we can characterize the stars that will have activity cycles is to look at the variation in their cycle length to variation to how that compares to their rotation rate. So what we see is that the faster a star rotates, the shorter its activity cycle. But this tends to happen on two main branches, the active branch and the inactive branch. And one of the theories is that these branches are fed by different dynamos. So dynamos are what responsible for the sun's magnetic activity cycle and magnetic activity in other stars. It's generated in the interiors of the sun's stars. And generally what happens is, so what we can see from this figure here is the colours are showing you the age of the stars. And what we also see is that on the active branch, the stars are much younger than on the inactive branch. And that's because as the star ages, its rotation rate slows down because of loss of angular momentum from stellar winds and magnetic braking. And so they become less active, stars become less active as they grow older. Now, if we plot the sun on here, it lies right in the middle of the two branches. And that has led a number of people to suggest that the sun is perhaps in transition from one branch to the other, although we're in a period where we're expecting changes in the solar dynamo. Now, one thing I would like to point out at this point, and it's a real bugbear of mine, is that this figure has no error bars on it. I showed you the difference between the last two in strength between the last two activity cycles. We also see quite a lot of differences in the length of the sun's activity cycle. So from, say, 9 years to 14 years. It's almost certainly true that these activity cycles vary in length as well. So it's a little bit up in the air whether this gap between the two branches is real or whether it's just an observational effect. So I said that the dynamos responsible for these magnetic fields are generated in the interiors of the stars. So what my research field is doing is using Helioseismology and Astroseismology to try and have a better understanding of the interiors of these stars. So Helioseismology allows conditions in the solar interior to be probed, and it does so using oscillations. So at any one time, there are thousands of oscillations traveling through the interior of the Sun. These oscillations sample different but overlapping regions of the solar interior, and so by looking at their properties, like their frequencies, we can build up profiles, such as how the temperature varies with depth, the rotation rate in the solar interior. We can even learn about the composition of the solar interior. So we characterize the oscillations in terms of three almost quantum numbers. For this talk, the only one that you need to know about is the harmonic degree, or L. So L tells us about the total number of node lines on the surface. So the simplest oscillation is just one that makes the whole surface of the Sun go forwards and backwards as a whole. This is the L equals 0 mode. We then get slightly more complicated combinations of forwards and backwards moving regions of the Sun. Now, the key part of this is, so these are acoustic waves, so they're sensitive to the temperatures and pressures in the solar interior. As they travel inwards, they're refracted by the increasing temperatures and pressures, and eventually they're fully refracted back out towards the surface again. Now, the depth they travel to before they're fully refracted can be characterized by this L, with the lowest degree modes traveling deeper in the solar interior than the high degree modes, which are trapped, like the red one here, which are trapped in the near surface region. And again, that's something I'm going to come back to later on in the talk. Now, we can observe these oscillations in two different ways. One of the ways is to look for the Doppler velocity movements of the surface. The other is to look for variations in brightness of the Sun or stars as the oscillations expand and contract the star. Now, we tend to take a relatively long time series of several months, perform a Fourier transform to create a power spectrum. And each one of the peaks that you can see in this power spectrum corresponds to a different mode of oscillation of the Sun. Now, this data was taken with unresolved observations of the Sun, so it only has the lowest degree modes, so those are the ones that travel right to the solar core. But you can still see there's a very rich spectrum of oscillations that we can use. You can see that the dominant modes have frequencies of about 3,000 microhertz, or periods of about 5 minutes. And then there's a drop in power on either side, and actually, as you'll see later on, this shape is very characteristic for solar-like stars. But because we're looking at the Sun at the moment anyway, we can make resolved observations of the Sun as well. So this is just showing you some power spectra for, so that allows us to see much higher degree modes. This is showing you the power spectrum of one particular degree in Doppler velocity and intensity. And then this power spectrum corresponds to one column on the plot over here, and each one of these ridges is containing thousands of modes. So we really do have a lot of information with which we can characterize the solar interior. But if we return to our unresolved data, and just for a minute zoom in on just two of the modes, you can see that they have a particular shape and structure. These are damped harmonic oscillations, and so when we create the power spectrum, they have a Lorentzian shape. So in order to extract the frequencies of these oscillations, we fit the red curves, which are based on Lorentzians, to the data. This tells us about the frequency, the amplitude of the oscillations, and the width of this Lorentzian tells us about how quickly the modes are damped. Now, if we take a time series that was observed at cycle minimum and a time series observed at cycle maximum and compare the two, you can immediately see there's a difference. So the blue is from activity maximum, the red's from activity minimum. And you can see that there's a change in frequency in between the two. There's also a change in amplitude, and actually the width of these profiles has changed as well. Today, I'm going to concentrate on the change in frequency between the two. So if we take an average change in frequency and plot that as a function of time, we get the figure here, which the black is showing you the change in frequency. The red is showing you the scaled version of the 10.7 centimetre flux, which is a well-known proxy for solar activity. So what we can see in this data is the 11-year activity cycle. We can see that the frequencies increase between cycle minimum and cycle maximum by around about 0.4 microhertz. Now this is a shift of around about 0.01%, so that's absolutely tiny, but because we have so many modes and because we can get their frequencies to such high precision, that shift, as you can see, is highly significant. Now there are two main reasons why we see this shift in frequency. The first is called the direct effect, which acts because the Lorentz force is the presence of the magnetic field introduces the Lorentz force, which is an additional restoring force. The second is a little bit more subtle, and it's because the magnetic field in the sun changes the internal stratification, and that then changes the frequencies of the oscillations. Now, if instead of looking at the variations as a function of time, we just consider cycle minimum and cycle maximum and subtract one from the other, we get a plot like this. So this is where I've subtracted the frequencies at cycle maximum, the minimum frequencies from the maximum frequencies. On this figure, the different colours are showing you the different degrees, where the reds and yellows are the high degree modes, so those are the ones in the near surface region, whereas the blues and purples are the ones that travel right to the solar core. What you can immediately see is that there's a dependence both on the frequency of the oscillation, but also on the degree of the oscillation. Now, we can very easily understand the degree dependence if we consider the mass of the solar interior that's being affected by these oscillations. So for the high degree modes that are trapped near the surface, there's less mass associated with that oscillation than the one travelling through the interior. And just as we all know it's much easier to move something light as it is to move something heavy, that means it's much easier for the magnetic field to perturb something with a smaller mass than a higher mass. And so if we scale the shifts by the mode inertia, which is determined by the mass of the interior affected by the mode, we remove that degree dependence and we're left with something that's dependent on frequency alone. This frequency, the functional form of this frequency dependence, tells us that we're looking at a very near surface perturbation. And that's because when the oscillations reach the surface, they're reflected back into the solar interior by the sharp drop in density. But they do so at different rates, slightly different radii, depending on the frequency of the oscillations, with the high frequency modes being reflected further out than the low frequency modes. And so if we do a model of a near surface perturbation, we expect a shape like this. I'm now going to go on to show you how we can produce similar figures to compare the last two activity minima, but just to motivate why we wanted to do that, as I've already said, that minimum the last minimum was referred to as being unusually deep and unusually long, and indeed there were more spotless days than in previous minima. The solar wind pressure was at a 50-year low, and if you just visually looked at the corona, it looked different from previous minima. But while some activity proxies, like the strength of the polar field, showed a clear difference between the two minima, so the red here is the minimum after cycle 23, and the white is the minimum before cycle 23. Other proxies, like the 10.7 centimetre flux, hardly show any difference at all. So if we consider the helioseismic modes, and here subtract the minimum before cycle 23, the minimum after cycle 23 from the minimum before cycle 23, and plot it as a function of frequency with the same colour scale as before, we can now see that there was a difference in strength of the magnetic fields in the two minima. And if we perform averages, just making use of the sheer number of modes that we have, we can see that that difference is highly significant. We can go one step further and we can fit a function to this curve just the same way as we can do between minima and maxima, and what we find is that within error bars we're getting the same functional form. And essentially what that's telling us is that in the two minima there was still magnetic field present, it's just weaker in the minimum after cycle 23 than in the minimum before it. Another way we can compare the activity cycles is just by directly comparing the helioseismic observations to other proxies like the 10.7 centimetre flux. So if you plot frequency against 10.7 centimetre flux for observations at different times, you get something that's approximately linear, and if you work out the gradient of that and then plot that as a function of mode frequency, you get this figure here. So this work was recently published by Rachel Howe. So in this plot, the different colours are showing, well, so the black is showing you data from Big Bear Solar Observatory, which was made observations during cycle 22. The filled symbols are then showing you observations from cycle 23, and the open symbols are showing you observations from cycle 24. And although these differences between the three cycles are small, because they're systematic, they are in fact statistically significant. And this is telling us that each cycle, the relationship between the interior and the atmosphere is changing from one cycle to the next. In my title, I posed the question whether the sun was in transition. Hopefully, I've shown you that we can use helioseismology to study cycle-to-cycle changes, and indeed we can look at very small changes in the sun's magnetic field. But because we only have a limited number of cycles of helioseismic data, in my mind, it's very difficult to answer whether the sun is in transition from these kind of observations. So other resource that we can look to is the stars. So I'm very lucky to be a researcher in a time when astroseismology is very much a boom subject. So much like helioseismology, astroseismology uses the natural oscillations of stars to learn about their interior. And because we can use the same data that people use for searching for exoplanets, we can look at those same intensity variations, do astroseismology. We have a huge wealth of data from Kepler and Corot, and even though those missions are no longer with us, TESS was launched very recently, and we have Plato on the horizon. So hopefully to convince you that we really are talking about the same kind of thing, these are two power spectra from two stars that are fairly similar to the Sun that were observed with Kepler, and you can see the rich array of oscillations again, and you can see that characteristic shape that we saw with the Sun's power spectrum. So because Kepler and Corot both stared at the same field of view for a relatively long period of time, in particular Kepler was looking at the same field of view for 4 years before the reaction wheels went, people started to see if we could do the same thing as we do for the Sun with other stars. They started looking for frequency shifts. This was the first published example that was appeared in 2010 by Garcia et al. And I want you to concentrate on the middle panel, which is showing you systematic variations in the mode frequency with time. This is one of the best examples from the Kepler data set, which is showing you a systematic increase in frequency with time. And these observations appear to correlate with magnetic activity proxies, also obtained from the same data set. And Angela Santos has published a nice review that I recommend you look at in the AppJ supplement series that systematically looks at a large number of stars that were observed with Kepler. But of course, with just 4 years of data, it's very difficult to observe full activity cycles, particularly for less active stars. And TESS unfortunately, isn't going to employ the same observing strategy. It's not going to look at the same patch of sky for any particularly long length of time. It's going to survey the southern hemisphere and then point to the northern hemisphere and survey that. So just for fun, we thought, what if TESS gets extended and it goes back to look at the same field of view again? Would we be able to detect any changes in the frequencies of the stars that it's going to look at? So just as an example, we took the TESS Astroseismic target list, which was put together by Matt Schofield from Birmingham, and Warwick created some synthetic data for this target list. So in this plot, we've got the surface gravity as a function of temperature, and the age for this sample, and we put a line through it that is somewhat arbitrary, but the aim of it was to separate it into main sequence stars and subgiants and giants. And so we then put together a recipe for predicting whether we might be able to see these frequency shifts. So in this recipe, we included the basic stellar parameters: radius, mass, surface gravity. We also included rotation rate. As I've said, the strength of a star's magnetic activity depends on its rotation rate. We've also included timescales related to convection. We've made some pretty big assumptions about how cycle length varies with rotation based on that figure that I showed at the start. And we've also assumed that there's a kind of smooth transition as the stars evolve to subgiants and giants. And what we see, so this first figure over here is showing you the size of the frequency shifts that we would expect if we were able to see a full cycle. What you can see is that there's a dependence on the temperature of the stars and also on the age of the stars, as we would expect. These figures over here are showing you what you might see. They're showing you only stars where we would see a significant frequency shift if the data sets were separated by 2 years. And we can see that there's a reasonable number of main sequence stars, but what really surprised us was the large number of giant stars. So based on this, we thought we'd go back to the Kepler data set. Most of the studies so far that have looked for frequency shifts in stars have concentrated on main sequence stars. We thought we'd go back to the Kepler data set and look at the giants. So from a sample of 16,000 red giant stars, we found over 3,000 with statistically significant frequency shifts in the Kepler time series. And this, we've only just found this in the last few weeks, but we're very excited by this result because we think it opens up a whole new realm of stars that we can use to study stellar activity. So that's all I want to say. So just to summarize, that we can use helioseismology to look at changes in the magnetic field, even very weak ones. We don't have enough cycles yet. We need more data. Basically, we need to observe the sun for much longer to be able to answer the question of whether the sun's in transition. While there is evidence for seismic frequency changes in other stars, perhaps we can get a bit more information from the red giants. Thank you for listening.
Thank you very much indeed. So open for questions. Well, I have one, and that is, do these frequency shifts, are they giving you any idea where the changes in the star are happening, in the core or in the surface?
So unfortunately, the acoustic modes are very much more sensitive to the near surface region than the core, because the sound speed in the core is very fast, so they don't spend very much time there. But that's kind of why we're so excited about the possibility of red giants and subgiants, because in these stars we can then start to see mixed modes, for example, which have much higher sensitivity to the core. And in fact, it's been able to be shown with some red giants and subgiants that there is the differential rotation between the core and the outer convection zone. So perhaps with these stars we might be able to get some more information.
Very good. Other questions or comments? Yes, please. Sorry, could you wait for the microphone?
Thank you. I was just wondering, in one of the graphs you showed that there was a relationship between the rotational period of the stars, and you mentioned that it slows down over time, and you mentioned very briefly some of the mechanisms, and I was just hoping you could maybe expand on what magnetic braking or something like that was.
Yeah, so, have I gone? Yeah, so if you think about what we know about the sun and the solar wind taking away as solar winds stream out, that's associated with magnetic fields, and that just adds a torque with time that slows the rotation.
Okay, any more questions? If not, then we thank you very much indeed. Thank you.